Welcome to lecture number 6. So in the last lecture, we discussed Noether's theorem, and we discussed how the symmetry of a theory leads to conserved currents. So let me quickly review how conserved currents and conserved charges are related. So suppose that we have a conserved current. That means this relativistic equation is satisfied. Here we are looking at the case of a current that is relativistically conserved. So this is a relativistic equation. In general, this equation need not be relativistic. So the current is a 4-vector whose time component gives the charge density and whose spatial components give the current density. So if you write this equation explicitly in terms of its components, then it becomes the time derivative of the charge plus the divergence of the current density is equal to 0. So this equation is known as the equation of continuity. Now, to get the conserved charge from the equation of continuity, what we do is that we integrate the equation over all space. So let's denote all space by sigma. Then we integrate this equation over sigma, and it's a volume integral. And we move the current part to the right-hand side. Now note that if I take the charge density and integrate that over all space, I get the total charge. So this is what we are going to be calling Q. If I take the time derivative of Q, Q only depends on time, or can depend on time, because from the expression of Q, we see that its space dependence has been integrated over. So the time dependence on Q can be written as now we assume that the limit of our integral is time independent. Then we can write this total derivative as a partial derivative. And then we can differentiate under the integral sign. So let us put the... So what we've seen is that the left-hand side of this equation is nothing but the time derivative of Q. This is what we have demonstrated. Now, what about the right-hand side? So the right-hand side is the integral over all space of the divergence of the current density. Now, if this is sigma, the sigma is a huge volume that we're integrating over. So the boundary of that would be a huge two-dimensional sphere, which is bounding all of space. So this is the boundary. Now, according to Gauss's divergence theorem, if we have the divergence of a vector integrated over a region of space, then that integral is equal to the integral of the vector that is we are taking the divergence of dotted with the area vector on the surface and integrating over the surface. So by Gauss's divergence theorem, we can write this as minus a two-dimensional integral over the boundary of all space, sigma, and the j vector dotted with the area vector. So this is the right-hand side. But the vector j is a function of our field and its derivative, perhaps. We are assuming that the fields are such that they go to zero as we go to the boundary of space-time. If that is so, j evaluated anywhere on the boundary of space is also going to be zero. And therefore, this right-hand side evaluates to zero. So if you put these in our integrated equation, we find that d of q, d of t, which is the total charge, is independent of time. That is, it is a conserved quantity. So this is the connection that I wanted to point out between a conserved current and a conserved charge.